geological timescale, and plate tectonics. Before we begin today, I want you to do something. Hold up one hand and spread your fingers wide. Now imagine that the entire history of the Earth, 4.5 billion years, is compressed onto the length of your arm, from your shoulder to the tip of your middle finger. In this scale, all of human civilization, every empire, every war, every invention from the wheel to the smartphone, occupies just the thin layer of dead skin at the very tip of that fingernail. That is deep time. That is what geologists work with. And today we are going to learn how to read it. The geological timescale is the framework geologists use to divide and organize the entire history of Earth into manageable units. Think of it as Earth's calendar, except instead of days and years, we use eons, eras, periods, and epochs. This timescale was built over 2 centuries of painstaking observation, rock mapping, fossil collection, and radiometric dating by scientists from every continent. It is one of humanity's greatest intellectual achievements. The geological timescale is divided into 4 major eons, from oldest to youngest. The Hadean eon spans from Earth's formation about 540 million years ago to roughly 4,000 million years ago. During this time, Earth was a molten volcanic world bombarded by meteorites, with no stable crust and no life. The Archean eon, from 4,000 to 500 million years ago, saw the formation of the first stable continents and the emergence of the very first life, simple, single-celled microorganisms called prokaryotes. The Proterozoic eon, from 2,500 to 541 million years ago, was a time of increasing oxygen in the atmosphere, the evolution of more complex cells, and the first multicellular organisms. Finally, the Phanerozoic eon, beginning 541 million years ago and continuing to the present day, is the eon of visible, complex life, and the one most familiar to us. It includes the age of fishes, the age of reptiles, the age of dinosaurs, and the age of mammals. The Phanerozoic eon is subdivided into 3 eras. The Paleozoic era, meaning ancient life, spans 541 to 252 million years ago. It saw the explosion of marine invertebrates, the colonization of land by plants and animals, and ended with the greatest mass extinction in Earth's history, the Permian extinction, which wiped out about 96% of all marine species. The Mesozoic era, meaning middle life, spans 252 to 66 million years ago. This is the era of the dinosaurs, the first mammals, and the first flowering plants. It ended with the famous Cretaceous mass extinction, likely caused by a massive asteroid impact, that wiped out the non-avian dinosaurs. The Cenozoic era, meaning recent life, spans 66 million years ago to the present. It is the age of mammals, grasslands, and eventually humans. A critical question in geology is, how old is this rock? Geologists use 2 broad approaches to answer this. First is relative dating, which tells us the sequence of events without giving exact ages in years. The most fundamental principle of relative dating is the law of superposition, proposed by Nicholas Steno in the 17th century. It states that in an undisturbed sequence of rock layers, the oldest layer is at the bottom and the youngest is at the top. Think of it like a stack of newspapers. If nothing has disturbed the pile, the oldest paper is underneath. The principle of original horizontality tells us that rock layers are deposited horizontally. So if we see tilted or folded strata, we know they were deformed after they formed. And the principle of cross-cutting relationships tells us that a fault or igneous intrusion that cuts across rock layers must be younger than the rocks it cuts through. The second approach is absolute dating, which gives us actual ages in years using the decay of radioactive isotopes. Every radioactive isotope decays at a fixed, known rate called its half-life. The half-life is the time it takes for half of the parent isotope to decay into the daughter isotope. For example, uranium-238 decays to lead-206 with a half-life of 4.5 billion years, making it ideal for dating very ancient rocks. Carbon-14 decays to nitrogen-14 with a half-life of about 5,730 years, making it useful for dating organic material up to about 50,000 years old. such as wood, bone, or charcoal from archaeological sites. By measuring the ratio of parent-to-daughter isotopes in a mineral sample using a mass spectrometer, we can calculate precisely how old that rock is. A third and enormously powerful dating tool is biostratigraphy, using index fossils to date and correlate rock layers. An index fossil comes from a species that lived for a relatively short, well-defined time period, existed in large numbers, and was geographically widespread. When we find the same index fossil in two separate rock outcrops, even on opposite sides of the world, we know those layers formed at the same time. Ammonites, trilobites, and foraminifera are classic examples of index fossils. Biostratigraphy was actually the primary tool used to build the geological timescale long before radiometric dating was invented. Now we turn to one of the most revolutionary ideas in the history of science, plate tectonics. The theory of plate tectonics states that the Earth's outer shell, called the lithosphere, is broken into a series of large, rigid slabs called tectonic plates, which move relative to one another over the underlying, partially molten asthenosphere. This movement, averaging just 2 to 10 centimeters per year, roughly the speed at which your fingernails grow, is responsible for earthquakes, volcanic eruptions, mountain building, ocean formation, and the distribution of continents we see today. The idea was first hinted at by Alfred Wegener in 1912, who noticed that the continents fit together like puzzle pieces and proposed that they had once been a single supercontinent called Pangaea. Though initially dismissed, his continental drift hypothesis was vindicated in the 1960s when seafloor spreading and paleomagnetic evidence confirmed that the plates are indeed moving. What drives plate movement? The primary engine is mantle convection. Deep within the Earth, heat from radioactive decay and residual heat from Earth's formation drive slow, churning currents in the mantle. Hot rock rises at mid-ocean ridges, spreads outward, cools, and sinks back down at subduction zones. This conveyor belt effect drags the overlying plates along with it. A secondary force is slab pull. The weight of a cold, dense oceanic plate sinking at a subduction zone actually pulls the rest of the plate behind it. Understanding these driving forces helps explain not just plate movement, but also why certain regions experience more earthquakes and volcanoes than others. There are 3 types of plate boundaries, each producing a distinct set of geological features. The first is a divergent boundary, where 2 plates move away from each other. As the plates separate, magma rises from the mantle to fill the gap, creating new oceanic crust in a process called seafloor spreading. The most famous example is the Mid-Atlantic Ridge, a 16,000-kilometer-long underwater mountain chain running down the center of the Atlantic Ocean. Iceland sits directly on this ridge and is one of the few places on Earth where a mid-ocean ridge emerges above sea level. Divergent boundaries on continents create rift valleys, such as the East African Rift System, which stretches through Ethiopia, Kenya, Tanzania, and Mozambique. Over millions of years, the East African Rift may eventually split the African continent, creating a new ocean. The second type is a convergent boundary, where 2 plates move toward each other. What happens at convergence depends on the types of plates involved. When a dense oceanic plate meets a less dense continental plate, the oceanic plate is forced downward in a process called subduction. The subducting plate descends into the mantle, generating intense heat and pressure. Water released from the subducting plate lowers the melting point of the surrounding mantle rock, generating magma that rises to form a volcanic arc on the overriding plate. The Andes Mountains of South America were formed this way. The Peru-Chile Trench, one of the deepest points on Earth's surface, marks the subduction zone offshore. When 2 continental plates collide, neither is dense enough to subduct easily. Instead, the crust crumples and thickens to form enormous mountain ranges. The Himalayas, including Mount Everest, the world's tallest mountain, were formed by the ongoing collision of the Indian and Eurasian plates, a process that began about 50 million years ago and continues today. The third type is a transform boundary, where 2 plates slide horizontally past each other, neither creating nor destroying crust, but grinding against each other along a fault line. This lateral movement generates intense friction, and when the stress is suddenly released, it produces earthquakes. The most famous transform boundary is the San Andreas Fault in California, USA, where the Pacific Plate slides northward past the North American Plate at about 5 centimeters per year. Major cities, including San Francisco and Los Angeles, sit near this boundary, making earthquake preparedness a critical public safety issue. Transform boundaries also occur in the oceans, offsetting sections of mid-ocean ridges. These are called transform faults, and they are responsible for many shallow but powerful submarine earthquakes. Plate tectonics is the unifying theory of geology, the process that explains why the Earth looks the way it does. Mountain ranges form where plates collide. Ocean trenches form where plates subduct. Volcanic island arcs, like Japan, the Philippines, and Indonesia, form above subduction zones. Mid-ocean ridges mark where plates diverge and new ocean floor is born. Rift valleys mark where continents are beginning to pull apart. Even the distribution of mineral deposits is controlled by plate tectonics. Copper and gold are often concentrated along ancient subduction zones, because magmatic fluids generated during subduction concentrate and deposit metals in veins and porphyry systems. Diamonds form deep in the mantle and are brought to the surface in ancient, stable continental cores called cratons, far from active plate boundaries. Understanding plate tectonics is therefore not just academically important, it is economically essential for mineral exploration and resource management. Let us bring everything together. The geological timescale divides Earth's 4.54 billion-year history into eons, eras, periods, and epochs, providing a universal language for describing Earth's past. Relative dating uses principles like superposition and cross-cutting relationships to establish sequence. Absolute dating uses radioactive decay and half-lives to give actual ages in years. Biostratigraphy uses index fossils to correlate and date rock layers globally. Plate tectonics tells us that Earth's lithosphere is broken into moving plates driven by mantle convection and slab pull. The 3 types of plate boundaries, divergent, convergent, and transform, create the mountains, volcanoes, earthquakes, ocean trenches, and rift valleys that define Earth's surface. Topic 4, we move into rock weathering and mineral formation, exploring how surface processes break down rocks and concentrate minerals into the forms we can mine and use. See you in the next lesson.